For more than 125 years, the American Physical Society has been advancing physics. As thousands of scientists meet in Minneapolis, the APS March Meeting continues to be the premier gathering of the best and brightest in the physics arena. Back for day 2 from the Minneapolis Convention Center, this is APS TV. Welcome back once again, everyone. This is APS TV, and I'm Audrey Godfrey.
And I'm Stephen Horn. We're your hosts for this week, and do we have a lot in store for you? You know, Audrey, yesterday we kicked things off with our one-on-one with Nobel laureate Anne Lehoulier, and today we will extend on that incredible body of research.
You're heading back to Sweden? Can I hitch a ride?
No, you know what they say, Audrey? They say that Nobel laureates at the APS are a bit like London buses. You wait for a long time for one to come along, and then 3 come all at once.
That's right. You're sitting down with one more Nobel laureate to hear more about quantum dots.
That's right.
The discoveries sometimes come out of frustrations, come out of a necessity. You don't know where it's going to go. So all these applications came out of nowhere.
And today we focus on the mission for science. As we both sit down with this year's APS president and CEO, we'll do a deep dive into the big issues facing humanity and get their perspectives.
The focus is this year is to strengthen our relationship with societies within U.S., but societies outside of the U.S.
And we go global today as we highlight the groups making big breakthroughs in physics research. See how global collaboration is key, Audrey. It's fascinating how these different institutions from around the world can collectively contribute to the new area of physics.
You're absolutely right. And you know what viewers will watch today is how from Jordan to Japan, physics is universal. And speaking of watching, there are plenty of ways for you to do so.
You can watch the programs right here in the Convention Center, on the in-house channels at several select partner hotels, on the March Meeting website and on the virtual platform, on the March Meeting app, on our YouTube and X social media channels, or you can scan the QR code right here. So let's get straight to it. Here in the studio to identify some of the biggest issues facing humanity and how physics is playing a role are APS President Young-Ki Kim and APS CEO Jonathan Bagger. Welcome. Thank you very much indeed for joining us today. We really appreciate it.
Yeah, thank you. It's great to be here.
Jonathan, let's get started with you. We are celebrating 125 years of APS, quite a milestone. What would you say has changed in the physics community over these years?
The physics community has grown tremendously over the last 125 years. For example, the first meeting of the American Physical Society had 36 people at it. And here we have something like 12,000 visiting us here in Minneapolis. But the physics community has also grown more international, more interdisciplinary, and frankly, more relevant to the world around us.
Young-Ki, as president, what has your focus been on? And how are you making sure that physicists address some of the issues of great societal importance?
I think it's very important to have very strong collaboration with the different disciplines and with the colleagues from around the world. So one of my the focuses this year is to strengthen our relationship with societies within U.S., but societies outside of the U.S.
So John, talk us through some of the priorities for APS in 2024 and how members here can get involved.
Clearly, one of the priorities this year is celebrating our 125th anniversary. And
Yes.
part of that is looking backwards. But a big part is also looking forwards to the important role that physics can play in the future. As part of that effort, Young-Ki has led a task force refreshing our mission, vision, and values. And so we can all really lean into these values because they're increasingly important in the world today. Also international, the basis of international collaboration are shared values.
So Young-Ki, how important has the APS been to you in your career?
My career, well, I started my relationship with APS in 1990 as a graduate student. Came to one of these APS annual meetings. So that became just my moment with the APS, and my relationship has grown until now.
And you've never looked back.
I never look back. This is amazing society. And as I said, as a student, one of my vivid memory is sitting next to director of Fermi Lab at that time, John Peoples, who happened to sitting next to me in the audience. And we were talking, and just that moment was just so thrilled and exciting. So, that's what APS has been providing to me and to our community.
John, we want to wrap up with you. You mentioned that as we are celebrating 125 years, not only are we looking back, but we're looking ahead. So can you kind of paint the picture for us? What does 2025 look like for APS? It's an exciting year ahead.
Yeah, the year 2025 actually marks the 100th birthday of quantum mechanics. And so APS is working with other physics societies around the globe to celebrate that occasion through events everywhere. The United Nations is on the verge of declaring this an official year, International Year of Quantum Science and Technology, and we are celebrating it by joining the March and April meetings together, where the entire physics community can come together in Anaheim, California, a year from now, and I hope to see everybody there.
Wow, I hope we're there too.
I do too. Looking forward to it. Thank you very much indeed for joining us. Really appreciate it. Thank you.
Thank you.
Thank you.
Continuing now with our theme of global collaboration, the Center for Quantum Engineering, Research and Education at TCG Crest is training future specialists for academia and industry from India and overseas.
The objectives of the center are twofold. First, to pursue cutting-edge research in quantum science and technology, and second, to provide high-quality education to students and to train them to carry out research in this important area in the future.
I am the first person to start to initiate this field in India, secure at TCG Crest, really one of the prime center that has been initiated over the last 2 years or so.
The primary research area that is being pursued in Secure at the moment is quantum computing, but we've taken initial steps to start research on quantum sensing, and we plan to work on quantum communication in the future.
The Center for Quantum Information and Quantum Biology is one of Osaka University's flagship research centers. Let's see how this research hub promotes international academic exchange in Japan and around the world.
The Moonshot Goal 6 will realize a fault-tolerant universal quantum computer by 2050.
We have a unique semiconductor technology named nanobridge. Nanobridge can drastically reduce the power consumption of semiconductor chip.
Single flux quantum SQ circuit is a superconductor-based digital circuit featuring extremely high speed and low power operation.
Radio over fiber is one of the promising technologies for transmitting the microwave signals from room temperature environments to cryogenic environments.
We have studied the control of large-scale superconducting quantum computers.
As we navigate through the project, we hope that we can make the pathway to the fault-tolerant quantum computer clearer and provides valuable insights that will pave the way for the next frontier in quantum computing.
Professor Munjiba Wendi was one of the initial developers of the quantum dot, and for his incredible discovery he was awarded the 2023 Nobel Prize in Chemistry. Professor Bawendi, such a pleasure to have you on the program. Thank you for joining us.
My pleasure.
So I was in the auditorium yesterday for your address. Give us a little bit of a flavor of some of the key points you were trying to make.
What I was trying to make is that the discoveries sometimes come out of frustrations, come out of a necessity, which is what our 1993 paper really was about. And then you don't know where it's going to go. So all these applications came out, we weren't planning on it, but came out of nowhere, it seems.
Tell us a little bit about what your major breakthrough was.
The major breakthrough was to find a fairly straightforward and simple route to making very high quality nanoparticles, these quantum dots. with nearly atomic precision using a synthetic method that could be easily scaled up.
And what is a quantum dot?
Quantum dot is a nanometer-sized particle semiconductor where when you put an electron in there, an extra electron, it obeys the rules of quantum mechanics. It's wave-like, and as a result, the properties are highly size-dependent.
Now, you won your Nobel Prize for chemistry, but you're at a physics conference, so why are you here?
I'm a physical chemist, which means I straddle physics and chemistry. I make things to study their physical properties. I've come to the APS meeting many, many times, and I go to American Chemical Society meetings as well.
So next year, as we all know by now, is the year of quantum. So are you looking forward to it, and what do you hope will come out of it?
I'm very much looking forward to it, and I hope that the broader public will gain an appreciation of how quantum is ubiquitous around us in our lives in so many applications already, and that there will be many more to come that will change our lives for the better.
It's my final question. A lot of young scientists here in the audience, and one of the great things about this meeting is they have the chance to meet people like you. So what would your message be to those young scientists?
My message would be that great discoveries are often fraught with failure at the beginning, but you have to keep the faith and follow your interests and your curiosity and keep going.
Thank you ever so much indeed for joining. It's been a real pleasure. Thank you.
My pleasure.
To Germany we go. Diatope was founded to develop synthetic diamond made in Germany for applications in quantum sensing and computing. Check out how this tailored diamond material is produced with defects.
We at Diatope, we are an international, interdisciplinary team of physicists, chemists and engineers, and we share the same vision of quantum technology soon transforming our everyday life. Located here in the campus of the German Space Agency, the QCI, the Quantum Computing Initiative, is one of our main customers, and we're developing diamond for quantum computers for them.
Diatope offers a suitable diamond material for applications in quantum computing and quantum sensing. Reliability, reproducibility, and steady supply are key here to bridge the gap between laboratory research, where unique diamond samples are used, and real-world products where we use uniformly produced diamonds. We at Diatope pursue a holistic engineering approach. This means we have all necessary fabrication facilities in-house, from CVD diamond growth over color center creation to quantum characterization and testing.
Our mission is to revolutionize diamond technology by delivering the enabling hardware, which are diamond quantum sensors and processors made in Germany.
To the Middle East now, and since the 1960s and 70s, facilities have used high-energy light sources to gain insights into physics, chemistry, and much more. However, in 2017, Sesame was opened in Jordan, giving the Middle East an opportunity to focus on the issues that matter most to that region.
The very short wavelength of the produced synchrotron light enables studying atomic and molecular structure of the material.
We can look at ancient artifacts, we can look at ancient archaeological treasures. The aim for establishing Sesame is to reverse the brain drain for scientists from the Middle East, in addition to establishing science diplomacy and be exemplary model for Science for Peace project in the Middle East.
Sesame is a synchrotron radiation source. By this, I mean we are producing light which is then used for measuring atoms in matter.
Sesame also represents a hub of knowledge and communication and training center for the students and the scientists.
There are almost 50 synchrotron facilities all over the world, and Sesame is the only one for us in the region.
The APS Medal for Exceptional Achievement in Research is the most significant honour awarded to recognise researchers from all areas of physics. This year's recipient, Stuart Parkin, joined us in the studio now. First of all, thank you very much for joining us.
Oh, thank you. I'm very happy to be here.
And congratulations.
Oh, thank you.
So let me start off. What is Spintronics?
Well, Spintronics is the idea that you can use the spin of the electron and manipulating that spin of the electron, particularly by creating currents of spin-polarized electrons, to create new materials, new devices, new phenomena that has use.
And how has that led to better data storage?
So a Spintronics sensor that I helped to invent and create in the 1980s enabled a 1,000-fold increase in the storage capacity of magnetic disk drives that even today, even though it's a 70-year-old technology, stores 70% of all digital data.
What's the legacy been of that research?
Well, I like to think that the world of today, which is purely digital, would not be possible without the spin valve technology that enabled this massive digital data storage.
And your current work, you're trying to make even better ways of storing data.
So the idea is that the disk drive is a mechanical technology, 70 years old. We want to replace it with a totally solid-state device with no moving parts, but in which we move the digital data using novel spintronic phenomena. I call this technology racetrack memory. I proposed it in 2002, but we think we're nearing the point where it could become a real technology. And the concept is you take magnetic nanowires on the nanoscopic scale. Each nanowire can contain hundreds of magnetic domain walls. These are tiny nanoscopic objects that can be moved up and down the racetrack synchronously by applying nanoscopic long current pulses. We can move the domain walls today at speeds exceeding 1 kilometer per second. So we can build devices with access time on sub-nanosecond timescales. So we can build the device by moving the data, which is unlike any other memory or storage technology today, without moving any atoms. We only rotate spins. And in this way we can build a very capacious, high-performance memory with no moving parts, therefore highly reliable memory, non-volatile memory technology.
What are some of the real-world applications this might have?
Well, real-world applications today, all the major companies of today, Microsoft, Google, Facebook, are based on digital data and accessing vast amounts of it to extract information that we ourselves individually cannot see. So this, for example, the major concepts today of artificial intelligence and machine learning are really based on being able to create and access and store and access that information very, very quickly. So I think with this new spintronic technology, the racetrack memory, we will improve the access time 1 million times compared to magnetic disk drives. So I think this is very exciting and will make these modern developments even more powerful.
Well, thank you ever so much indeed for joining us. It's really fascinating. Thank you.
Thank you so much.
Singapore's quantum engineering program, launched in 2018, supports translational research focused on industry challenges and initiatives to nurture a quantum ecosystem.
We are now in a maturation phase where we understand what the science is, we know what the opportunities are.
Our method of quantum imaging and quantum spectroscopy can find application in many areas, such as biomedicine, material research and characterization, and sensing.
Thermal light is heat, such as the light generated from sunlight or LEDs. For our case, we managed to generate a light source that is very bright.
I make integrated photonic circuits to generate entangled photons and use electromodulators to control these photons.
We have actually formed a national quantum office to help to coordinate all these research investments. At the same time, plan and drive a development of a national quantum strategy.
Yesterday we had the pleasure of hearing from one of the Nobel laureates awarded for research into attosecond light pulses. Today we're keeping that conversation going. Absolutely delighted to be joined by Pierre Agostini, also 2023 Nobel Physics Award winner. It's such an honor. Thank you ever so much indeed for joining us today.
My pleasure.
So having spent all your life, working, researching in physics, what was the feeling like when you won that award?
The first feeling was surprise. I mean, I know I know a lot of people, and I would have given the prize to them rather than me. So, well, I understood at the end that they awarded the experiments and founding experiments. We'll live with it.
What was it that attracted you to become a physicist in the first place?
Well, I wanted to do math. They sort of discouraged me and saying, yeah, it's too difficult. So I took physics.
What is it that's kept you going all these years?
Sometimes you have to get lucky to do an experiment. My first good experiment, I think, was back in '79. Before that, I was just doing experiments on multiphoton ionization, looking at ions. And for the first time, we looked at electrons. So we had to build a spectrometer, and we did it. And for the first time, it was successful.
There's thousands of young people here at the conference, and a lot of them will have been to hear you speak yesterday. What words of advice would you have for them?
The advice would be, well, if you can, do fundamental research. And don't worry about the applications and about practical results.
Well, thank you very much indeed for taking the time to talk to us. We greatly appreciate it. So thank you and congratulations once again.
Thank you.
Now we cross the Pacific to Kyoto. The Kyoto Institute of Technology has been developing a theoretical approach to quantum computing that is 10 billion times more tolerant to errors than current theoretical models. Their method brings us closer to developing quantum computers that use the diverse properties of subatomic particles to transmit, process, and store extremely large amounts of complex information.
Quantum computing is a revolution of computers. Quantum computers can increase our quality of life, QOL, since QC can be applied to complex problems that cannot be solved by classical computers. One of the goals for the moonshot is to develop a fault-tolerant quantum computer, FTQC. We focus on research topics related to qubit controllers and error correction systems above qubits. Scalability is one of the important things to extend current quantum computers with less than 1,000 qubits. The highly integrated error correction system is a key feature to scale up the number of qubits to realize an FTQC.
Staying in Japan now, the Moonshot Goal 6 R&D projects involve NEC Corporation bringing together multiple research teams from private companies, universities, and laboratories in Japan, all with the aim of realizing a superconducting, fault-tolerant quantum computer.
The Moonshot Goal 6 will realize a fault-tolerant universal quantum computer by 2050.
We have a unique semiconductor technology named NanoBridge. NanoBridge can drastically reduce the power consumption of semiconductor chip.
Single flux quantum SQ circuit is a superconductor-based digital circuit featuring extremely high speed and low power operation.
Radio over fiber is one of the promising technologies for transmitting the microwave signals from room temperature environments to cryogenic environments.
We have studied the control of large-scale superconducting quantum computers.
As we navigate through the project, we hope that we can make the pathway to the fault-tolerant quantum computer clearer and provides valuable insights that will pave the way for the next frontier in quantum computing.
Particle accelerators have been the primary tool of particle physics for over 60 years now. Well, the International Linear Collider is the next advancement in accelerators and will be the complementary electron-positron collider that could help answer some of the most fundamental questions of all time. What is the Higgs boson? What are dark matter and dark energy? And does supersymmetry exist?
International Linear Collider is a 20-kilometer long particle accelerator that we hope to build. The idea is to accelerate electrons and positrons and annihilate them and make the heaviest, most mysterious particles that we know in nature, the W boson, the Higgs boson, and study their properties.
The whole design of the ILC aims to achieve its scientific goals with the minimal amount of resources. At the very heart of the accelerating technology is energy efficiency. This is why we use, for instance, superconducting structures in order to accelerate the particles.
These big goals in high-energy physics motivate the construction of really novel technologies. And there are lots of people around the world who are very eager to do this physics, and we're trying to work together.
Scientists from about 50 countries collaborate, and we need to make everybody work together, produce the best ideas, and still keep a coherent design.
What an incredible day of seeing these international organizations and the work that they're doing, Audrey.
It really is pretty fascinating to see how physics transcends borders and language barriers to tackle those big picture issues facing humanity that you were talking with President Young-Ki Kim about.
She brought a bunch of great points, and that's why we're continuing our international focus for tomorrow's episode. You'll hear from some of the International Year of Quantum and how everyone can benefit from this tech revolution.
Okay, now you have my attention. We can all benefit. Remember, if you missed any part of today's episode, you can find the latest APS TV episodes on the TVs here at the Convention Center, on the in-house channels at several select partner hotels, on the March Meeting website and on the virtual platform, on the March Meeting app, on our YouTube and X social media channels, or you can scan the QR code here.
Audrey, with all those ways to watch, there's no excuse to miss us. That does it for today too. Like I said, we'll see you right back here tomorrow for our International Year of Quantum discussion. Have a great one.